Welcome back to class 17. What we covered in the last video is we talked about the second law of thermodynamics and how we could only go in one direction for many processes. And that's often most associated with work and heat, that we can use work to generate heat. But in order to generate work from heat, we need some kind of device. And we talked about that heat engine and how that functions. Now I want to talk about one of the big takeaways in all of this, and that's thermal efficiency. We want to have some type of measurement for how good of a job we're doing if we're going to create work from heat. And that efficiency is always going to be less than 1. And that's part of the second law, right? That we're always going to have less work than heat put in, right? So we have this heat flow coming in to generate work. Well, how well did it do? So we'll say, and we can put dots in front of these if we want to, or we can just make them a quantity. So this is out, excuse me. I don't know why I put it in. So this is, and we should say it's net out. Sometimes I'll leave that, I'll just say net, the net work. And this is going to be the high heat coming in from our source, right? So from here, from the high temperature reservoir, and it's going to come into the device, and we're not talking about what's going on inside, but this is an example of a heat engine, so we can see what's taking place inside. And we're extracting this work, and then we're dumping some down into the low reservoir. So we could say, just from the simple things that are crossing right here, that the conservation of energy tells us that we were going to get that the work out is going to equal the QH minus the QL, right? So if there's conservation of energy, that has to be true. So we can replace this with a QH, and I should be consistent with my dots. So there are rates. And then what you're left with, notably, for the efficiency, 1 minus Q dot, I guess, divided by QH. And this is an important concept right here, something to keep in mind, that in order to make a high efficiency, right, you need to have this quantity be as small as possible because you're subtracting from 1. If they were to equal each other, you'd have a 0 efficiency. If we could somehow get rid of the amount of extraction or the throwaway, we would have 100% efficiency. But impossible to do in either case. So well, that's not impossible to do in the first case. You could make them equal to each other and make this 0. But if we can minimize this, we can improve efficiency. But also, if we could maximize this, we could improve efficiency. So that's an interesting version of the equation, of the efficiency equation, and it's all based on the heat engine concept. Now we were able to go backwards, and we introduced this the other day. And I'd say backwards, where I'm saying that we're going to go from a low temperature to a high temperature. And how do we do that? Well, we actually sort of trick it and introduce some work involved here, so that we're able to move. So that perhaps this is actually going to be a higher temperature than this. So heat flows into it. And then this is a higher temperature than this, so heat flows out of it, right? So these are 2 different regions. This might be inside the refrigerator or the freezer, and this is the back of the refrigerator, or this might be your air conditioner. This might be the room, and this is the outside space right here. So we're able to move from a low temperature to a high temperature, and in doing so, we have to introduce work right here. And in this case right here, once again, if you were going to do an energy balance, you'd say now the work in was going to be equal to, still going to be QH minus QL. And if you needed to believe that, you could just say that you'd say, well, how do we get QH? Well, we would add this power into the Q low and that would generate the QH. So it would be, we would just flip the thing over to the other side, and we would believe in this. So we take in a similar manner to what we did up here, right? So this falls under the category of efficiency, or the measure is what you want over what you paid for, right? You want work, or you want power, and what do you pay for it? Well, you pay for it in heat, and that could be fuel, right? You can take the equivalent heat of the fuel that gets burned, or how much capacity for heat generation. So it's often called the heating value of a fuel. You could think of that as being what you're paying for. So you're actually paying money for that heat. So down here in the same idea as a measure of the performance of a refrigerator or freezer, we have something we could call beta now, and we go what you want over what you pay for. Once again, but here, interestingly enough, this value up here is always less than 1. This is often, and mostly is, greater than 1 right here. So let's take this. What we want is we want heat extracted. So that's going to be QL, and I'll make a dot because it's a rate. And then here's work, and this is in. And I could just go ahead and replace the QL. Did I do that wrong? Yeah, I'll replace this guy down here. So I'll go QL. That's what I want. Divided by QH minus QL. And then if we were to turn this around, just like the other one, but now we have to keep the thing in the denominator, we'd say we have QH minus, divided. Oops, I can't transcribe. QL dots are going away right here. So this is what's called often the coefficient of performance, and this is the refrigeration one, right? The coefficient of performance. And you can see that this is going to be a value greater than 1, because well, silly me, forgot to put that in there. Okay, sorry. Yeah, so you can see that this is this, because of this ratio right here, and we're subtracting 1 from here. This is going to be greater than this one, right? If they were the same and you had 0 in the denominator, it wouldn't explode, wouldn't do any good for you. But you know, this is always going to be larger than that right there. So therefore, this is going to be how well you did. And you could have values greater than 2, as much as 4, maybe even higher for this as typical. So I don't have one shown right here, but you could just think that, like, just change what the purpose of this is. So now let's say this is inside your home and this is outside. And we're drawing heat from the outside, and now we're exhausting it into your house. This is called a heat pump, right? So a heat pump is we have different goals in a heat pump. So what they have is a coefficient of performance, and we'll go HP, and in our book we go beta prime, and that's going to be QH is what you want over what you paid for is also here. So this is usually done with electricity or whatever, because you usually have a motor and it's being run, so you're paying for that, but you want to move some heat. And so a similar level of what we just had here a second ago, H, but now we're going to replace that with, because we have the same thing over here, so we have QH, Q dot H minus QL, because that hasn't changed. But what will change is you'll have 1 over 1 minus Q, I'm going to get this right, QL over QH. And so this is your coefficient of performance. And this too is going to be greater than 1. If you had the same values though, note that you get this just from math, just from the algebra of this. If you had the same values of QL and QH in the flow, here's going to be the relationship between a unit that's used as a refrigerator versus a unit that's used as a heat pump. So we will make a end to the video there and start some examples. They're simple examples. Maybe I'll cover them in two examples in one video.